Imagine the universe as an immensely dense and hot point, roughly the size of a grain of sand. This point contained all the energy and matter that would eventually form everything we see today. Around 13 billion years ago, this tiny speck began to expand rapidly, an event we now refer to as the Big Bang. This expansion wasn't just an explosion in space, rather, it was the expansion of space itself. In those first moments, temperatures soared to unimaginable heights, and as the universe expanded, it cooled down. This cooling allowed quarks and electrons to form. When conditions became favorable, these quarks combined to create protons and neutrons, forming the building blocks of atoms. Over millions of years, clouds of hydrogen and helium, the simplest elements created during this period, began to coalesce under gravity's influence, leading to the formation of stars and galaxies. The light we see today from distant galaxies can be traced back to this primordial event, giving us a glimpse into the universe's early years. The Big Bang theory also points to the grand abundance of these light sources and the cosmic background radiation that fills the universe. And our galaxy is our own. This radiation serves as a snapshot of the infinite universe, revealing information about its composition, temperature, and expansion. In this way, the Big Bang theory not only explains how the universe began, but it also opens a window into the fundamental processes that continue to shape it today. The theory of cosmic inflation emerged from the need to explain certain puzzling aspects of the universe's early development. Scientists recognized that the observable universe is remarkably uniform. This means that despite vast distances between galaxies, the cosmic microwave background radiation, a remnant from a hot, dense state shortly after the Big Bang, is evenly distributed. However, this uniformity raises a question. How could regions so far apart be so similar if they had never been in contact? To address this conundrum, cosmologists propose that an incredibly rapid expansion, or inflation, occurred just after the Big Bang. This expansion would have stretched those small, uniform regions across vast distances in a fraction of a second, smoothing out variations that created homogeneity in large-scale structure of the universe, including how galaxies are distributed in clusters and orbits, aligns well with predictions made by inflation theorists. It suggests that the structures formed from a small initial inhomogeneity before inflation. Finally, studying gravitational waves and crystals in space-time generated by immense cosmic events has provided another potential layer of evidence. If inflation generated gravitational waves as theorized, observations can validate the inflation hypothesis. Thus, the theory of cosmic inflation not only began as an elegant solution to a significant question, but has also been supported by consistent observational results that fit hydrogen atoms eventually clump together under gravity, forming the first clouds of gas. As these clouds continued to gather mass, they sparked the birth of the very first stars. It's fascinating to note that these stars were mainly composed of hydrogen, and in their cores, through the process of nuclear fusion, they began to transform hydrogen into heavier elements like helium and beyond. This transition was crucial. The marks a pivotal moment in the history of the universe, occurring roughly 300,000 years after the Big Bang. During this time, the universe had expanded and cooled to the point that electrons could combine with protons to form neutral hydrogen atoms. Before this phase, the universe was a hot, dense plasma filled with free electrons and protons, creating a fog that light could not penetrate. As temperatures fell, these electrons found their place in stable orbits around protons, allowing photons, light particles, to travel freely. This transition is significant because it made the universe transparent for the first time, allowing light to move without scattering. This light would eventually become what we know today as cosmic microwave background radiation, a faint glow that fills the universe and provides us a snapshot of its early stages. The impact of the era of recombination on cosmic evolution is profound. It set the stage for the formation of the first structures of the universe. Once matter became neutral, it could begin to clump together under the influence of gravity. This led to the formation of primordial gas clouds, which would eventually evolve into the first stars and galaxies. The release of the cosmic microwave background radiation also had important implications for cosmology. By studying this radiation, scientists can gather information about the conditions of the early universe and the rate of its expansion. Additionally, this era helped establish the large-scale structure of the cosmos, influencing how galaxies and galaxy clusters formed over billions of years. Essentially, the era of recombination was not just a moment of change, it was a crucial catalyst in the unfolding story of the universe, shaping the landscape we observe today. The transformation of the universe from a hot, dense state to the cool, expanding cosmos we observe today was rooted in a fascinating journey that began shortly after the Big Bang. Initially, the universe was an incredibly complex environment filled with energy and radiation. This primordial state could even form distinct particles. Everything was made of mixed, high-energy conditions. As the universe began to expand, a fundamental change. Imagine the rapid inflation of the lunar system. At this early phase, just moments after the Big Bang, space itself expanded dramatically. This expansion caused the temperature to drop, allowing for the formation of basic particles like protons, neutrons, and electrons, akin to tiny building blocks. As the universe continued to cool, these particles combined to form light atoms, primarily hydrogen and helium. This era is often referred to as the recombination era. When the temperature became low enough for electrons to be captured by nuclei, the universe transitioned into a more structured entity. This significant event allowed photons, or light particles, to travel freely through space, creating what we recognize today as the cosmic microwave background radiation, with faint particles like over billions of years, as the universe expanded further, gravitational forces began to act. Regions of gas and dark matter started to clump together, giving rise to stars and galaxies. This ongoing expansion continues to this day, as galaxies drift further apart from one another, marking the evolution of a Thus, what began as the intense and hot peak of energy transformed from gradual cooling and expansion into the vast universe filled with stars, planets, and galaxies we explore and study today. Galaxies are vast collections of stars, dust, gas, and dark matter, all bound together by gravity. The formation of galaxies begins in the early universe shortly after the Big Bang. Imagine the universe as a fresh canvas with tiny fluctuations in density occurring throughout the expanding material. Over eons, these fluctuations allow regions with slightly more matter to attract surrounding materials, igniting a cosmic process that leads to the coalescence of gas and dust into the first proto-galaxies. As these early structures gather mass, they evolve. They can collide and merge together, leading to the dynamic formation of larger galaxies. Throughout this process, stellar winds and the gravitational influence of these young galaxies bulge. These arms often house star-forming regions filled with young, bright stars. In contrast, elliptical galaxies resemble elongated spheres, exhibiting a smooth, featureless appearance. They typically contain older, cooler stars and less interstellar gas, meaning lower rates of new star formation. Then, there are irregular galaxies, which defy any simple classification owing to their chaotic shapes. They often contain a mix of young and old stars and can result from gravitational interactions or collisions with other galaxies, leading to their unpredictable appearances. Finally, there are not emit or absorb light, making it invisible and detectable only through its gravitational effects. Think of it as an unseen framework that guides the formation and behavior of galaxies. Without dark matter, the universe as we understand it would look vastly different. As galaxies form, they gather mass from clouds of gas and dust. Gravity pulls this matter together, but for galaxies to develop their spiral shapes and maintain their structure, they require much more mass than what we can see. This is where dark matter becomes crucial. It exists as a vast halo surrounding galaxies and extending well beyond their visible edges. This halo contributes the gravitational pull necessary to hold galaxies together and to ensure they rotate at the speeds observed, preventing them from flying apart. When we observe clusters of galaxies, we notice that the visible mass does not account for the gravitational effects at play. The outer regions of galaxies are rotating faster than they should if only the visible matter is present. The additional gravitational effects provided by dark matter indicating that there is much more mass influencing the astronomical structure than we can detect with our instruments. Moreover, dark matter plays a vital role in the larger scale structure. It acts as a scaffold that influences the distribution of galaxies and clusters, shaping the cosmic web we see today. Areas of higher density where dark matter collects attract ordinary matter, leading to the formation of galaxies. Thus, without dark matter, galaxies wouldn't just be different. Many of them might not exist at all. Thus, without dark matter, galaxies wouldn't just be different. Many of them might not exist at all. Its presence is fundamental to understanding how galaxies evolve, interact, and remain stable through cosmic time. Soon,